So last time we saw this diagonal algebra, and that's actually helped us to realize the universal semigroup C-star algebra as a cross-product algebra. And for that, I need to introduce this notion of semigroup dynamical system. So in the classical sense, a dynamical system usually is just a group acting on a topological space. But in terms of operator algebra, people realize, well, your action on your topological space can be realized as the action on the continuous function on the topological space. So oftentimes it's tied to an action, a group action on a commutative algebra by these automorphism on your C-star algebra, basically C of your topological space. And well, then if you can act on a commutative C-star algebra, how about you replace it to just any C-star algebra? So that's the idea of using generalizing the dynamical system in terms of operator algebra. You can do the same for a semigroup. So here, let me give you the definition. So a semigroup dynamical system is very similar. You have a semigroup P acts on a unital C-star algebra A by an action, which we call the P action. The only difference is that in group, when you try to act on the C-star algebra, because your action need to be invertible, your group is invertible, so your action has to be by automorphism of your C-star algebra. But the semigroup, you don't have automorphism because you don't have inverse. So what you end up with is something called the endomorphism. Okay, so this is the endomorphism here. So the endomorphism just means it's just a homomorphism from A to A. It doesn't even need to preserve the identity. It's just a map which continues preserve the group operation. All right. And what you have is that whenever you have such a dynamical system, you can talk about its representations. So a covariant representation is essentially just a representation that kind of encodes your dynamic. Okay, so covariant representation is usually given by a pair where the first part is a representation of your C-star algebra. Okay, so let's just say because A is, I'll assume C-star algebra are unital. Let's assume this pi is a unital star representation. And your V is a representation of your semigroup. Okay, so we don't even need to assume P is a quasi-lattice order, but all the example we have will be quasi-lattice order. But anyways, so they have to encode your dynamic. How you encode the dynamic in a representation is that your action. So if you want to represent something, say alpha P of an element A, so let's represent something X by this semigroup action, is actually implemented by this conjugation by the isometry VP. Okay, so it satisfies these conditions. So this is kind of how you encode the P action in terms of operators. So now this action, this pretty algebraic condition now becomes some kind of operator condition. Okay, so you have these representation. And whenever you have these covariant representation, you can now build a universal C-star algebra. So the universal C-star algebra of these dynamic, so alpha P, AP alpha, is just essentially, well, let's just write the notation is cross product. This is essentially the C-star algebra generated by some universal representations, IA, of your C-star algebra A and the IP of your semigroup P. So here the IA IP is kind of a universal covariant representation. So by universal, it just really means, in other words, for every covariant representation that you have, let's say pi V onto some B of H, you can always find by the universal property, you can always have a homomorphism from your universal object to this B of H that maps the thing to what you expect to be. Okay, the universal one for A can map to pi of A. The universal one for the semigroup get mapped to the corresponding V of P. Okay, so this is a star homomorphism of C-star algebra. All right. So this is the universal C-star algebra. And if you just recall, we introduced the Nika covariant representation of your semigroup. Uh, the universal semigroup C-star algebra we define it as the universal C-star algebra of isometric Nika covariant representations. Okay, so in other words, you can think about it as a C-star algebra generated by a universal representation of your semigroup. Okay, so X is inside the semigroup. Okay, so VU here is the universal one. You take the direct sum of all the Nika covariant representations, and that's of course a universal object. And Nika kind of, when he studied this algebra initially, he conjectured there has to have some kind of cross product structure of these C-star algebra. And it turns out it's true, and is clarified by this paper by Laika and Rayburn a few years later. And the C-star algebra P is essentially just given by the covariant representation of some diagonal dynamic. Okay, so let me just clarify what I mean. So now if you consider the following, so if you consider this d lambda, the diagonal algebra we defined in the last video, and I want to have an action on this diagonal by the shift. So the alpha p of my 1x is essentially just shifting this x by p, okay? So this one is going to be a semigroup dynamic. And if you think about what happens when you have a isometric Nika covariant representation of your p, well, that will just implies that, well, you can define a representation for 1x, which is just equals to vp star, vx star. So what you have is the pi of the 1 of px, which is the action by p. This is just equals to vp pi of 1x vp star. So every Nika covariant representation, you kind of corresponds to a covariant representation. Okay, so that leads to a covariant representation pi v. Okay, covariant representation of this dynamic. Okay, and the converse is also true. Okay, you can convince yourself, because if you have a covariant representation, then all of these pi of 1x has to be vx star, because 1x is basically alpha x of the identity, okay, the constant 1. So the pi is a unital representation, so using the covariance condition, you get a pi of 1x is vx star. Using pi as a representation of the d lambda, the diagonal algebra, you get the v is Nika covariant, okay? So because of this kind of correspondence, then what you have is that when you take the universal, you imagine you take the universal one, basically building the direct sum for each category of either Nika covariant for P or the covariant representation of your semigroup dynamic, you essentially get the same thing, okay? Because you're also both taking a direct sum. And so this essentially just tells you the universal semigroup C-star algebra has this diagonal structure. Okay, so this is equals to the isomorphic to this semigroup cross product. Okay, and moreover, there's one more thing. Okay, so if you consider what happens to the universal one, and it also contains a diagonal algebra. Okay, so if you consider VU, the universal Nika covariant representations, and you can consider the diagonal algebra, let's say DU, basically spanned by all this VUX star. Okay, so they're sitting inside the C star universal one of the semigroup. Okay, well, this universal one, well, this from last time we kind of see this VUX star. They're a family of projection that satisfy this Nika's condition. So they give you a representation of the d lambda. Okay, so this pi of VU defined by, if I map 1x to the VUX star is a representation of the diagonal algebra d lambda. And because your VU is a direct sum of all the Nika covariant representations, so it certainly contains a copy of the left regular representation. And the left regular representation is faithful, and so you direct sum a bunch of other stuff, it's still going to be faithful. So this pi of VU is faithful. Okay, so pi of VU is faithful. And it's not surprising now is that this du is just isomorphic to the d lambda. Okay, so you kind of identify the vu star with the corresponding lambda star. Okay, so the nice thing about this is that well, the universal one, even though it's a really big algebra because you take a direct sum of a bunch of other representations, the diagonal is the same as the left regular one. Okay, the diagonal is really small. Okay, it's very concrete. You can think about this diagonal subalgebra sits inside the universal one. Okay, so this d lambda, sometimes we just pretend its diagonal is the same as the d lambda, so they are inside. And this is a really important property, and we're going to show why this is the case probably next week.